So, hi everybody. I'm going to be giving a talk about natural language processing. And because it is language, everybody understands it, but not everybody wants to process it in a way that computational linguists process it. Just asking you for a show of hands, how many of you are data scientists, machine learning engineers? Oh, aspiring data scientists, machine learning engineers? Yeah, that's great. Are there any linguists in the audience? Yay, quite a lot. Great. So I'm going to be talking about language, and this is the obligatory XKCD. This is how I was introduced to that webcomic, and I've loved it ever since. But the point that he's trying to make here, that computational linguistics is an ill-defined field. Anything that has to do with NLP, you've done one NLP project, you can call yourself a computational linguist. For me, it's my actual degree. I am from Germany, and I've always loved languages. I speak 3 languages, and I apologize if my English is not good. It's my 3rd. Okay. So this talk was inspired by my attempts to mentor people who try to do an NLP project. Data science bootcamp graduates who just wanted to expand their portfolio. I'm going to just briefly introduce the main concepts of NLP as it relates to machine learning. And I would like to explain and show why traditional rule-based NLP is still relevant. The main part of the talk is going to be some recipes with the open source library called SPACY. You can think of it as a brief appetizer with a tweet, and then the main course is going to be processing a YELP review, and then a dessert, a mini dessert, is multilingual topic modeling. After each recipe, I'm going to sum up some do's and don'ts, or you can think of it as peaks and pitfalls, and hopefully some of it can be useful for your NLP project. All right. Linguists like to think of languages as living, ever-evolving organisms. For data scientists, it's inconvenient, unstructured text blob of data. And you would like to extract some information for it using some tools like pandas. But for something as complex as languages, a familiar tool like a hammer may not be appropriate. You need something like a power tool. What you want to extract from your unstructured blob are some useful nuggets of information. I'm going to call them tokens, and it can be anything from words to phrases, sentences. Depending on your goal, you may be only interested in some of them, so you'll have to transform them, count them, and discard the rest. Extracted tokens can be labeled for future processing by machine learning algorithms. And those labels are provided by traditional linguistic methods. In this case, POS stands for parts of speech. But you can also have labels like geopolitical entities and organizations. So once you've labeled your tokens and counted them, you have to prepare them for machine learning algorithms. This process is described as feature extractions. So you basically have to vectorize them. And some tokens are going to be more important than the others, depending on your task. Just a very simple overview of machine learning algorithms. If you have no labels whatsoever, all you can really do is take your text blobs and combine them into bigger text blobs. When you have labels, you can use various machine learning algorithms for classification. For example, spam, not spam, or sentiment analysis, positive, negative, or neutral. But the most lucrative algorithm, of course, is deep learning. And deep learning algorithms are often applied as a black box, so you don't necessarily know what's going on inside, but it is very accurate. And beyond the scope of this talk is how to scale your first NLP projects when you really want to apply deep learning. I want to show how to do the very basic case on a small data set, as small as possible. And it's up to you and infrastructure engineers to scale it up. Okay. This is the NLP pyramid of sadness. What you see on the left is a traditional view of linguistics. you have different fields of linguistics, and they kind of all build on top of each other, and the level of complexity increases from bottom to top. It starts with the sound of a human language, and then you have words and different word forms. Morphology deals with those. And on the sentence level, the set of grammar rules and constraints that defines the sentence, how grammatically correct it is, this is the linguistic discipline called syntax. But the most interesting one and challenging one is semantics and pragmatics. They both deal with meaning. Semantics deals with meaning on a level where you can look up things in the dictionary. Pragmatics, on the other hand, takes everything else into account, the context, everything that is not said but universally understood, the shared cultural references. Where the pyramid kind of tips is the way NLP is applied in the industry, because semantics, as the most challenging, this is where the money is. Natural language understanding is where a lot of research is happening nowadays, both in academia and in industry. Okay. For those of you who have never seen syntax and any example of syntactic trees, this is a real example of how a syntactic parsing is happening, and I wanted to show it on a more contemporary sentence and not really nice examples. So this is a phrase, this party is going to be lit, and it's a verb phrase, and this verb has two dependencies. A noun phrase, this party, which is the subject of the sentence, and it has a complementary clause, be lit. It has a lot of meta information like auxiliary verbs and particles. Okay. So why is NLP a hard problem? Data produced by humans is very messy. The 26 levels of the English alphabet don't even begin to cover it. Sometimes you have special characters, could be encoding errors, and it could be treated as garbage to filter it out. But when you're processing social media text, you may be interested in that garbage, like links or hashtags. The same words pronounced differently can mean different things, and this is something called homonyms in English, like tear in eye, your dress will tear. So there's a lot of ambiguity. And then the same words and phrases, when they're used in a sentence, can change their meaning. Like this agreement is about principled compromise, not a principle compromised. The difference here is just a suffix. Those corner cases are very interesting academically, but in practice, you will probably never see them. So all you need really is more text, more data. And this is the NLP divide between small and big data sets. Once you have big data, you don't care about linguistic ambiguity. The law of large numbers says that whatever errors you have, it will be evened out. So you invest in better annotation tools. For your first personal NLP project, you are very likely not to have enough data. So every word, every token counts, and you invest more time and research into pre-processing tools. And this is where open source NLP libraries come to your rescue. The library I would like to introduce you, if you're not familiar with that, is called SPACY. It's an open source project maintained by exactly 2 people in Germany. The idea of this NLP pipeline is to get you from unstructured text blob to something that you can extract a lot of attribute from. And you do it through a pipeline that starts with a tokenizer. You split your text blob into something meaningful. And then it goes through a part of speech tagger, a syntactic parser, named entity recognition, and you can plug in your own attributes that you would like to extract. This is highly customizable. All right. The creators of SPACY call this pipeline a recipe as well, and you can combine them in whatever way you like and try to apply them to really difficult text examples, like a tweet. If you look at this tweet example, if you don't know her, Mara Averick on Twitter, she has created her own visual language to describe data science tools, and she uses tweets, she uses emoji, lots of GIFs, and Archie references and basketball stats. As you can see, it's actually not a lot of text, so it's going to be a little bit more challenging, but I can still show a typical NLP pipeline. All right, I'll start with tokenization. And here it becomes interesting because you can think of it as splitting a sentence by white space or punctuation, but it's not always as trivial as that. There are some languages they don't even have white space between words, like Japanese. Or my example is in German you have compound words that can be very long, and when you translate them, it's a group of English nouns, not just one. So Einkommenssteuererklärung would be income tax return. And this is why part of speech tagging becomes more interesting, because syntax allows you to group those tokens in a meaningful way through the means of syntactic parsing. And for the tweet, the emoji become interesting because they should be organically integrated into this process of grouping. They are part of the meaning of the sentence. And this is why the nice to have optional step that is very interesting is chunking, which is just grouping of nouns. And it's nice to have, it does improve the accuracy of your machine learning model. And when you think about it, chocolate bar, bar exam, wine bar, space bar, those are all very different kinds of bars, and it only makes sense in the context. Okay. So I'm not going to show you the full notebook. I'm just going to show you the relevant parts that are not part of the typical NLP pipeline. If you're interested in the typical pipeline, I would refer to the SPACY documentation, which is really nice. What I'm doing here is I'm creating a specialized dictionary for emoji, because if you'd like to use this pipeline for sentiment analysis, you would like to know how do you define your emoji, which ones are positive, which ones are negative. So this is my little emoji dictionary. And I'm looking at some of the outputs. What I'm interested in, I'm filtering out everything that is alphabetic words, not alphanumeric, just really alphabetic. And everything else, which could be Twitter handles, links, hashtags, and emoji. And I'm creating some sort of a very simple sentiment score by just looking up my emoji. And this is an example of the parse tree, and what I'm looking for here are dependencies. You see that the first star is classified as a pronoun. The second star, the glowing star, is part of a noun phrase, which is good. That's what I'm looking for. A glowing star tool. So this is almost like a human language. Okay. Some pitfalls with that recipe. You have to be really careful with encoding. Emoji are Unicode, but they can also be ASCII or UTF-8. So some special characters, you have to make a decision early on. Do you treat them just like punctuation to be filtered out, or do you assign meaning to them? And some part of speech tags can be wrong. So don't rely on the built-in syntactic trees. It's always better to look at your output. Some best practices: before you do anything in SPACY, you have to identify the language. To load the appropriate model, SPACY has several for several languages. English is the best, obviously. And then filter or remove non-alphabetic characters. You're going to have a lot of noise. Nice to have is a custom dictionary, but this takes a lot of time. Chunking the noun phrases, it's something that a lot of people do. And there is a simple way of doing it when you just rely on built-in tools, or you can write your own rules for chunking. Something not to do is assume that everything you have in a text is going to be simple English. NLP isn't an English-only speaking club, and what works for the New York Times in the clean, simple English may not work on Twitter at all. Off-the-shelf models that SPACY provides work for standardized text well enough. Okay. My second recipe is a Yelp review, and especially for Yelp reviews, I've discovered that people cannot spell. And it's very hard to extract actual meaning from that. So I'm just going to read this review for you. We drove 30 minutes out of the way to get some dessert and ordered a ton to go, only to find that they didn't give us what we ordered. What we did get was not good. We called and they refunded us $4. Ridiculous. Don't waste your time or money there. Sixth course right around the corner is way better. So it's a very negative review. As you can see, it's 1 star. And it is my favorite chocolate store in San Francisco, so I'm surprised. I want to know, why was this review negative? If I was the business owner, what was it? Especially a rude employee? Maybe the price was too high, maybe it's the quality of products. A lot of things that you can look into that it's not necessarily part of the standard dictionary. So I'm going to be looking at tokens that are named entity, like names, numbers, places, everything. The pipeline becomes a little bit more complicated compared to the tweet. So I'm trying to improve the built-in tokenization here for English, and one of the things that I've often noticed people don't think about are contractions. It's relatively simple to expand them, and it does improve the tokenization, because without that what you get is just nonsense tokens, just one letter T. You can also normalize units of measurements, or you can try to create a more normalized base form for nouns. Then the next part is filtering. I would like to remove some words that don't carry any actual meaning. Those are very common. It's like the, and, of, all kinds of preposition in English. There are various lists of stop words depending on the language. And then the main part, the exciting part, is the named entity recognition. So I will be looking at things like geopolitical entities, dates, numbers, and try to identify them. Small note on normalizing. You have 2 versions of normalization. You can do stemming and lemmatization. So because my data set is so tiny, I have to map all the tokens to the base form, and I have to be very careful about it. Stemming is basically chopping off some suffixes to get to the base form. It works well enough for most of the words, but it can produce some nonsensical tokens. The example is for employee. If you cut off the suffix, you get something that can be read as employer. And for irregular noun and verb forms, it just doesn't work at all. Lemmatization is doing things properly by looking things up in a dictionary like WordNet. You can still use stemming if you'd like, but you just have to keep in mind its precision and recall. What do you care more about? Lemmatization is obviously more accurate. Stemming works well for English, but it may not work at all for morphologically rich languages like Russian. Lemmatization is still relatively fast with SPACY, so it's not a performance issue, and SPACY doesn't have a stemmer, so you don't really get a choice. Okay, this is probably hard to read, but I'm happy to answer questions about the code, about this Jupyter notebook. What I'm filtering out here is a bunch of things: punctuation, stop words, and I'm not very interested in nouns, so I'm filtering them out as well. The rest of tokenization is happening under the hood. SPACY does it relatively fast and is very accurate. And then the next step is I'm looking at named entities like money, date, and everything that I can find in the text. And instead of just printing them out for me to look at, I'm actually collecting them in a list for future processing. Okay. This is the output of the built-in SPACY visualizer. And you can see some of the results. Some things were classified correctly. Most of the numbers, time, quantity, money, you can find it all in that visualization. The named entity recognition struggles with capitalization. So there are some false positives. Apparently, ridiculous is a geopolitical entity. And way, because everything is all caps, is an organization. One problem is that a local named entity was not recognized at all, sixth course, because both parts of that noun chunk are common English words. And SPACY wasn't trained on American or even local San Franciscan local chocolate shops. Some pitfalls for this recipe that I have to think about is expanding contraction can be ambiguous. Apostrophe S can be possessive or contraction, and sometimes it's a different verb could be I had or I would. Spell check is very tempting to use, but you have to be very, very careful with that because always be wary of autocorrect. The name of the library itself, SPACY, is always autocorrected to space. And before using any spell check suggestions, it's important to check whether the word is in the dictionary, because a spell checker will try to correct every word, so don't run it over the whole data set. And then this is the main problem I've seen people struggle with, named entity and lowercase. Sometimes it's difficult to disambiguate a rose by any other name. It smells just as sweet, but a rose is a common name. And a lot of people don't capitalize their own names. Capitalization is crucial. You have to have a plan B for when it fails. So this is where the order of operation becomes really important. Named entity recognition before lowercase. Expanding contraction is optional, but it improves tokenization. And you may want to create your custom rules for phrases or negation, especially for sentiment analysis. Not good or good. Okay, the pipeline operation is important. Before you lowercase all the things, make sure you've extracted all the information you want. And sometimes it will still fail anyway. This is why ignoring domain knowledge is not a good idea. Sometimes you may want to download the list of local businesses and train your own named entity recognizer. It's relatively easy to do with SPACY. All right, so I am at the third recipe, and just like dessert, it can be skipped. So I'm just going to explain the idea, what's going on, but before I show you the results, there will be no more code. I'm happy to stick around here and show you the actual code, how it's all working. The idea is I wanted to show an example of topic modeling, and we've seen an example of topic modeling yesterday at the talk. What I'm doing here, I don't have a collection of documents. I have a toy corpus. There are only 2 articles that I'm looking at. And this is an article about starting with SPACY. This is an article in English, and this is the same article but translated into Spanish. I have extracted the text of this article, split them into paragraphs, and because it's a direct translation of the English text, I'm going to assume those documents are more or less parallel, so I can compare them paragraph by paragraph. So this is the pipeline, putting it all together and kind of connecting it all in one big picture. Tokenization, normalization of tokens, filtering, chunking, some named entity recognition as well. And then I would be counting the resulting tokens per paragraph and using these counts in a bag of words approach as input to topic modeling. And last step is I will be comparing the highest ranking topics provided by the library called GenSim, and I'll compare them for English and for Spanish. And I apologize that my Spanish isn't very good, but the idea is if both articles are about the same topic, we're going to see some similarities. It's not going to be identical, but you should be able to identify the topic. So here are the results. I have excluded some of the things, but kept the names of the library like NLTK and SPACY. And for Spanish, I can see palabras means words. So yes, it is about natural language processing. And PLN in Spanish is the same as NLP, as far as I know. So the topics in English is object, doc, NLP, pre-processing, text, tasks. So you can see even for the tiniest corpus, the topic modeling was still relatively good. And this is the surprising part. Now you can only improve the accuracy of this clustering. And those clustered topics can be used something like hashtags for blog posts, or you can use them as labels for your data set. Okay, just very quickly, I mentioned a bag of words. What is it actually? A bag of words does not contain any actual words. If I had to explain it like, explain like I'm 5, think of Scrabble. You have Scrabble tiles in a bag, and you can take them out and stack all the tokens that are identical. You can stack them, and then you get the frequency. So this is the bag of word approach. The tokens or tiles are completely independent. It becomes more interesting when you actually put the tiles into a sequence to form the words. And then you see that it makes sense that some tokens will appear more often together. The context becomes more important. And the frequency of tokens that are very, very common, they're actually punished. You're more interested in rare words because then your score gets higher. And this approach of combining the tiles is word embedding, where context is really important and you're looking at the whole sentence or the whole paragraph. An example is doc to vec or the original word to vec. Okay, so this does not really make sense without looking at the code, but just some best practices for topic modeling if you choose to do that as your first NLP project. Try to use n-grams, not just one word, but chunks of word, bigrams, trigrams. And as the metric for word frequency, like mentioned yesterday in the talk, TF-IDF is the right metric. Term frequency, inverse document frequency, instead of chi-square test or log likelihood ratio test. Words are measured on a categorical scale, so they're either there or not. It's binary. But some tests take into account that a lot of documents share words among the documents, and this is where TF-IDF is more sophisticated. Chi-square test, when you apply to two different collections of documents, the assumption is they don't share any words. They have nothing in common. And it's just simply not true for most human languages. I'm almost at the end of my presentation. I have some more slides that I'm happy to discuss, like in a small unconference upstairs after lunch. But here are my main takeaways that you'll hopefully remember. NLP is a hard problem. It's called artificial intelligence for a reason. And it is very messy. You have to actually look at your output and improve it in many different steps. And words are not numbers. You cannot run nice statistics on them. There is no t-test for NLP. So looking at your input and your output and just trying to predict potential problems, it's very helpful. And this allows you to customize your NLP pipeline if needed. And domain knowledge, not just linguistic knowledge, but just domain knowledge in general is very important. Just like I mentioned in the example for named entities, sometimes you need a list of local businesses and then you plug it in as your custom vocabulary. And this would yield you better results than trying to improve just your machine learning model. And there are lots of NLP tools out there. You can try to pick the right one for you that works for your project. I have compared NLTK and SPACY, and SPACY is the best for me. For performance reasons, for accuracy reasons, it's just the fastest. And then NLTK was developed for more academic purposes. SPACY is trying to be industrial strength NLP that is easy to use and very fast. Okay, but choose the right tool for you and just don't be afraid to experiment with language. You will see the results if you speak the language. And even if you don't, there are still some things you see and you can ask native speakers. It goes back to my takeaway. Domain knowledge is important. Sometimes it's easier to ask the speaker of Spanish whether the results were good or not. Okay, so thank you very much.